Assalamu alaikum, dear students. We're back with another video lesson. In the previous video lessons, where we're talking about translational and rotational equilibrium, and we've solved a lot of questions related to that. Today we'll talk about a new concept, or we'll begin with a new section, and there is a new concept, of course. We're going to talk about rotational dynamics. The first thing that we're going to start with is Newton's second law for rotational motion. Now, if you remember last year in grade 11, we had Newton's second law for translational motion. And what was Newton's second law for translational motion? We said we were saying F net that is equal to mass times acceleration. In other words, if we have an object with a certain mass, and if you apply a net force acting on this object here, then this object would have or acquire a certain acceleration here. That is called Newton's second law, but don't forget that is for translational motion here. For translational, you can say. Now, this here, because we're dealing with rotation or angular stuff, so if we have an object like a disk, let's say, if you apply a certain force on this one here you can see that, of course, there's the axis of rotation. If you apply a certain force on this, and we've also learned about the moment of inertia, this object would have a certain moment of inertia t here, so there will be a certain angular acceleration for this one. In other words, we can say Newton's second law in rotational motion here, this is what is going to be. Instead of, let me just rewrite this one here. We said the second law for translational, it was net torque, it was net force that is equal to mass times acceleration. But now, you can say Newton in rotation, Newton's second law in rotation, right? Rotation. And instead of force, we have the net torque. It's the same equation, but instead of using translational quantities, we have angular quantities. Now, guess what we're supposed to write instead of the mass? We have moment of inertia, well done. And instead of acceleration, we have angular acceleration. This is called Newton's second law in rotational motion. Now, if that is the equation, how can I define this one? Can I say the net torque, or we can say Newton's second law in rotation states that the net torque acting on an object, it is equal to the product of the moment of inertia and the angular acceleration. If not, you could say states that the moment of inertia, Newton's second law, the net torque, it is equal to moment of inertia of an object multiplied by the angular acceleration of the same object, of course. Now, we know that the net torque, we've previously learned that it is measured in Newton meter. So we can say this is the unit for Newton's second law for rotational motion. That would be the net torque measured in Newton meter. We know that the angular or moment of inertia is measured in kilogram meter squared, and then the angular acceleration, it is measured in radian per second squared. But if I'm going to combine this one here, we can say kilogram meter squared and then multiplied by radian per second squared in here. But don't forget, we said radian is a dimensionless unit, so once you're going to combine this with any other unit or multiply them, we'll just cancel, or we're not going to write the radian here. So this is what is going to be in this case. So there's no radian over the second squared. So now we can say Newton meter, it is equivalent to kilogram meter squared over second squared. And I believe you remember this. We said this is the same or equivalent to the net torque, to the torque that we've learned in the first section of chapter 2. I hope you remember this one. So that is the Newton's second law in rotational motion here. All right, clearly now, net torque is a vector quantity. Moment of inertia is a scalar quantity. That means it has no direction. It can not be negative or zero. If not zero, because if the object is rotating, there will always be a certain moment of inertia. And then the acceleration can also be, it is a vector quantity. These two will always be in the same direction, by the way. Don't forget, just as the same that we were saying in grade 11, that the net force and the acceleration will always be in the same direction. Now, let me tell you a little bit more regarding Newton's second law of motion here. So we can say the net torque, it is equal to moment of inertia times angular acceleration. We've also learned that how do we find each one of these separately if they're not given directly in questions once they require for one of these variables here. For the net force, we've learned that in chapter 1, we could say. In chapter 2, section 1, we said whenever we have the net torque, you can always use the net torque that is equal to force times distance. If you don't have the force, you have the mass instead, we can say mg instead of the force times the distance. Sometimes instead of the distance, the radius is given. That is also fine. You can write distance as a radius here. All right, as for moment of inertia, we know that we had different shapes here. We said it was a fraction, a number times mass times the radius squared. It could be the length squared if it is a rod or something like that. And there was a number here. I'll just write c instead of that number. So whatever the number is, this c, you can say it is a constant which represents the number. Now another thing, what about for the angular acceleration? Angular acceleration can, of course, can be found in different ways. One of the ways we can say omega final minus, let's just write a bit smaller here, omega final minus omega initial divided by delta t. This is one of the methods we can use to find angular acceleration. There's another method here. We can say it is also equal to tangential over the radius here. And if you did not have the tangential and you wanted to find tangential acceleration, you can say v final minus v initial over delta t as well. So these are all equations you can use to find whichever, for example, that you want to find here, especially whether for angular acceleration, moment of inertia, or the net torque as well. Okay, once again, the net torque is a vector quantity. This is a scalar, and this is a vector as well. Now, before we solve any question, let me give you some study tips regarding the net torque in here. We can say the net torque can be both positive or negative since it is a vector quantity. Okay, when is it positive? If the rotation is counterclockwise in here. And the net torque can be negative if the rotation is clockwise here. So counterclockwise, it could be negative if it is clockwise in here. But the good thing is, all the questions that we have, it consider the object always rotating counterclockwise. So we don't have to worry about this clockwise direction at this point right here. So we can say, once again, if the rotation is counterclockwise, it is positive, and that is the case where this book is always considering the rotation is counterclockwise. If the direction is given or mentioned, that's a good thing you could tell. If it is not given, we just care about the magnitude of the net torque, and that would be it at this point here. So, since the book only considers or concerns with the rotation that is counterclockwise, we're going to do that the same here. So we can say the net torque can be positive and negative as well. Remember, we're talking about counterclockwise rotation, all right? If the net torque or if the rotation is counterclockwise, don't forget. So we can say omega, at that point it is counterclockwise. If that is the case, the net torque will be positive if the angular acceleration is positive. And when is the angular acceleration is positive? If omega final, it is larger than omega initial. Can I say if that is the case, the object must be speeding up? So whenever the object is speeding up, we can say the net torque must be positive. When will it be negative? Watch this. We can say the net torque is negative if the angular acceleration is negative, right? And when do we have, or when there will be angular acceleration, when the angular acceleration will be negative, that is if omega final, it is smaller than omega initial, and that is the case of, we can say, slowing down, okay? Or even when the object is stopping, that is the same case in here. So watch this. The object is rotating counterclockwise. If the object is speeding up, the net torque is positive, all right? So angular speed is positive if the rotation is counterclockwise. If the object is speeding up, in this case, of course, omega final will be larger than omega initial. If that is the case, then acceleration is positive, which makes the net torque to be positive as well. But if the object is rotating counterclockwise and slowing down, don't forget, if it is slowing down here, the rotation is still counterclockwise. But if the object is slowing down, that means omega final, it is smaller than omega initial. If that is the case, angular acceleration will be negative, which makes the net torque to be negative as well. And this is why if it is negative, the object is going to slow down and then until perhaps it might even stop. So these are what you need to know at this point here. There's one more thing which I would like to mention here, and that is this. If the question says there is no net torque acting on the object, do you remember this? This is one of the conditions for equilibrium, we can say. The rotational equilibrium. If the net torque is 0, then angular acceleration is 0. We can say the object is at equilibrium. Okay, object is at equilibrium. Equilibrium. So at this point, two things happens here. We can say because the angular acceleration or the angular acceleration is 0 or the net is 0, we can say if the object is at rest, okay, then the object will remain at rest. Remain at rest. That's first. When we say it is at equilibrium, that is the first thing, that if the net torque is 0, then if the object is at rest, it will remain at rest. But if the object is moving, or you can say rotating, moving, when we say moving, it is rotating, obviously. Rotating, then the object must rotate at a constant speed. Okay, it must rotate at a constant speed. Constant speed. In other words, we can say omega initial must be equal to omega final. Don't forget this. And then the last thing that we have, we always know that air, what about air resistance and friction? Air resistance and friction. What do you think they'll do to objects here? Friction. We know that air resistance and friction always tend to slow objects down, right? And if, watch this, imagine if an object is trying to rotate or rotating counterclockwise, what would be the direction, or what will air resistance and friction do? They try to slow down. If they try to slow down, then we can say the net torque, that is, or the torque that is produced by air resistance and friction, will always be negative if we consider, because they will always be opposite to the direction of the rotation or the motion. And in other words, we can say air resistance and friction will always produce a negative net torque. But once again, these are for cases where the object is rotating counterclockwise. All right, now let's go back and solve a few questions. Perhaps maybe the first thing you need to know is Newton's second law. That is the definition. You need to know this definition. It is very important. It says that the net torque on the object is the product of the moment of inertia and the angular acceleration. You can also add that is measured in Newton meter as well. Measured in Newton meter. All right. And here's the equation. We said the net torque is equal to moment of inertia times the angular acceleration. There's one thing that I forgot to mention, actually. Up to this point, how many cases for Newton's second law of motion have we studied so far? We can say up to this point, we've studied 3 cases for Newton's second law of motion here. What was the first one? First one was grade 11, where you can say the net force, okay, the net force, it is equal to what? It is equal to mass times acceleration. We'll use this equation whenever we have translational motion. In other words, whenever an object is moving in a straight line, if we ever needed the force, the mass, or the acceleration, this is the equation that we're going to use, by the way. Whenever the object is moving in a straight line, we have an object, an example, a question that an object or a certain mass is sliding over an incline. That is still considered Newton's second law of motion in translational because the object is moving in a straight line here. Okay, now the second Newton's second case where we studied Newton's second law of motion was for rotational motion. We said circular motion. We said if an object is moving in a circle, like a car, like a mass or whatever, we said if an object is moving in a circle, there will be centripetal force, if you remember. And then there was a centripetal acceleration too. So Newton's second law for circular motion, we call this one Fc. It is equal to, or was equal to, mass times acceleration. But what acceleration? Centripetal acceleration. Don't forget, this is for circular motion. For circular motion. Whenever we have an object moving in a circle, this is the equation you'll need to use. And we said this centripetal force was provided by many different forces. Now, the third type or case where we studied Newton's second law of motion, and that is for rotational motion, when we have an object like a certain object, like a whole disk together, not just a point on that disk, let's say, or a point moving in a circle. No, the whole thing, it is rotating. If that is the case, Newton's second law for this one would be the net torque instead of just the force, because it is rotating. And instead of the mass, we'll use moment of inertia. Instead of acceleration, we'll use angular acceleration. These are all the three laws, or we can say all the cases where we can use Newton's second law of motion. Once again, translational, circular, and rotational. For rotational motion, we can say. All right, now let's go back to the other one. Perhaps maybe it is time to start with some questions. All right, so this is the equation, and this is how you can find each one of these. And you might wonder, what is this Ft times the radius here? That is, if you have a disk, this force that is acting on a disk at a certain distance here, you can call this one. This is a force, sometimes we say a tangential force. The reason why tangential, if you remember, in chapter 1, we said if we have an object moving in a circle, but if it decides to go in a straight line, we call this one tangential speed. So tangent, that'll be a straight line or a line that touches the circle only at one point. So you can call this force just F, or F tangential times a distance that produces a torque. If not, you could just call it F times the radius. That'll be just fine. Okay, and then for moment of inertia, we'll use this. For angular acceleration, we'll use, these are the equation, omega final minus initial divided by the time, or tangential over the radius, or final. For the tangential, we can use v final minus initial divided by the tangential. All right, that is for this one here. I think now the study tips that I believe I've covered all these points, but I'll just go through them real quick. It says, when do we use Newton's second law of rotation? Whenever we have velocity tangential, whether, let's say, angular acceleration tangential or angular acceleration, moment of inertia, and delta t. Or whenever we have the net torque, moment of inertia, and either speed or acceleration, whether they are for translation or rotation, because you can convert it to rotational if given here. We said that the net torque is positive. When is positive? If the rotation is counterclockwise. If that is the case, the angular acceleration will also be positive. There's another case we said if the object is speeding up. In other words, if omega final is larger than omega initial, then the angular acceleration will be positive, which makes the net torque to be positive too. The net torque will be negative if the rotation is clockwise. That is one way, even though the book does not concern this one a lot. In that case, the angular acceleration will be negative. There's another case we can say the angular or the net torque will be negative if the rotation is, watch this, the rotation is counterclockwise, but omega initial is larger than omega final, then the angular acceleration will be negative, and then which makes the net torque to be negative. If the net torque is negative, that means the object will always tend to slow down. Remember, when the object is rotating counterclockwise and you get a negative torque, that means the object is slowing down. And we also said that if the net torque acting on the object is zero, if the object is rotating, it will rotate with a constant angular velocity. If it is at rest, it will remain at rest. Point number 7 says rotating objects have inertia. Well, if something has mass or inertia, then if it is going to rotate, that inertia would lead to or become a moment of inertia. All right, what about 8? We said air resistance and friction will always produce a counteracting or opposite torque. In our case, said if the rotation is counterclockwise, then air resistance and friction tend to slow the object down, which means they are in the opposite direction. This is what it means, counteract. All right, now we have, but it's time to have a question here. It says, student tosses a dart using only the forearm of his rotation of his forearm to accelerate the dart. The forearm rotates in a vertical plane which is about an axis at the elbow joint. The forearm and the dart have a combined moment of inertia Let's write the information that is given here. Okay, so here. All right, it says the forearm on the forearm on the dart have a combined moment of inertia. So here's moment of inertia, which is your 0.075 kilogram meter squared. About the axis, and the length of the forearm is 0.26. The length, you could say, or the radius, doesn't matter, or you can even call it the distance. This point makes no difference here. Okay, so these are all the same at this point. It is 0.26 meter. The dart has a tangential acceleration. Remember, this is tangential acceleration, and that is 45 meter per second squared. Just before it is released, what is the net torque? Watch this, and you can underline this. It says, what is what? What is the net torque? And because we have moment of inertia and then tangential acceleration, and the question says, what is the net torque? In that case, I believe you could just find the net torque in here. So the net torque is unknown. So how do you find the net torque? We said that the net torque, it is equal to, since it is rotation, moment of inertia times angular acceleration. But here's the thing. Do I have the moment of inertia? The answer is yes. But what about angular acceleration? No, I have tangential instead. So how can I find angular acceleration? We know that angular acceleration, it is equal to what? It is equal to tangential over the radius, yes? What is the tangential equal to? I think this is too small. Let's write it here, perhaps. All right, I'll just bring this one closer. Here's angular acceleration. We said angular acceleration, it is equal to tangential over the radius. What is the tangential? It was 45, yes? Divided by the radius. What is the radius? It is 0.26. Find the answer here. Angular acceleration equals to something. Let's see what it is equal to. It is equal to 173. 173. 173. What is the unit? That is radian per second squared. Now, can I find the net torque acting on the yes. So moment of inertia was 0.075 times the angular acceleration 173. Okay, now you can find the net torque in here. Whatever it is going to be this much Newton meter. Let's just see what is it equal to. It is equal to 13 Newton meter, and that is how easily you could do this. It's pretty easy if you know what is given and what is unknown at this point here. Okay, now let's solve another question. See what else is given here. Okay. Now we have another question here. Says the potter's wheel has the shape of a disc. Now these questions have been in Wazari several times, so I really need you to be aware of this one and make sure you practice enough until you fully know how you could do this. Okay, so let's solve this one together as well. It says the potter's or a potter's wheel that has the shape of a disc. Now I need you to underline this one for me. It says it has the shape of a disc. What is the moment of inertia of a disc? And it has a radius on this one as well. So the shape of a disc, let's say here's a disc, and we know that the moment of inertia of a disc is equal to 1/2 mass times radius squared. All right, so we have a radius. What is the radius? It is 0.5 meter. What about the mass? The mass is 100 kilograms. It is freely rotating at 50 revolves per minute. Oh, that's interesting. So now we have angular speed, which is 50 rev per minute. Don't forget that is chapter 1. We're not allowed to use rev per minute. We have to convert that into radian per second. Very good. It says the potter can stop the wheel. So let's just write it down. If the potter can stop the wheel, this must be initial, which is 50 rev per minute in here. Okay, and then it says it can stop the wheel. That means omega final will be 0. Okay, in 6 seconds. So can I say this is delta t? In 6 seconds, so that'll be delta t, 6 seconds. By pressing a wet rag against the rim. So the first part of the question says, what is the angular acceleration of the wheel in here? So angular acceleration, it is equal to what? Angular acceleration, it is equal to omega final minus omega initial divided by delta t. All right, now what is omega final? It is 0 minus what is omega initial? It is 50 rev per minute, but can I use rev per minute? The answer is no. Every rev is 2 pi, every minute is 60 seconds, correct? So now 50 times 2 pi divided by 60 seconds, let's see what that equal to. 50 multiplied by 2 pi, 50 multiplied by 2 pi, and then divided by 60 seconds. The answer is going to be 5.235, we can say, or 5.24, we can say. 5.24 if I wanted to round it up, divide by 6 seconds in here. So let's see what is angular acceleration equal to. Negative 5.24 divided by 6 seconds. The answer is going to be equal to negative 0.873. Angular acceleration, negative 0.873. We could just say 87. That is going to be radian per second squared. That is the first part of the question here, says what is the angular acceleration. The second part says how much torque does the potter apply to the wheel? How much torque does the potter apply on the wheel? So let me just write the second part in here. How much torque does the potter apply on the wheel? So now we can say the net torque, it is equal to moment of inertia times angular acceleration. Once again, do we have moment of inertia? The answer is no, but I have an equation where I can find it here. So moment of inertia, just plug these numbers into the equation. Remember, it is a disk, so the equation is 1/2. That is 0.5 times the mass is 100 times 0.5 squared. So that is 50 times 0.5 squared. And the answer is going to be 12.5. So the moment of inertia is 12.5 kilogram meter squared. Now just bring this number back into the equation here. 12.5 times the angular acceleration, which is negative, just write the negative here, negative 0.87. All right, multiply this two number times negative 0.87. The answer is going to be 10.87. We can say it is negative 10.9 by rounding, if you want to say. If not, you could just keep it as 10.87. And of course, don't be surprised if you see this one as negative 11 Newton meter as well. So it is one of the options here, whichever you see in the choices. Of course, you can, according to that, you can either round it up or leave it as it is in here. That is how easy you can solve this question right here. Okay. Now, I believe it is time to move to another question here. All right, let's move on to another one. Okay, question 2 says a bicycle. All right, let's clean this. It says a bicycle tire of radius 0.3 and a mass of 1.5 kilogram is rotating at this much radian. What torque is necessary to stop the tire in 2 seconds? Once again, so it is this is the radius, this is the mass of the bicycle wheel, and rotating at this much, this is angular, we can say initial. Why initial? Because it says what torque is necessary, so the net torque is unknown here. To stop the tire. When it says stop the tire, that means omega final must be 0 in order to stop, and this is delta t, which is 2 seconds. Consider the tire as a ring in here. Now remember the tire or the bicycle tire, because the shape of a bicycle tire looks like a ring, so even if they don't say a ring, you need to know it is equal to mass times radius, mass times radius squared only. So make sure you know how to do that. All right, so let's solve this one too. Net torque right away, it is equal to moment of inertia times angular acceleration in here. So once again, net torque, I'll just do that in one step. The moment of inertia for a bicycle wheel, that is mass times radius squared times angular acceleration, it is equal to omega final minus initial divided by delta t. Now all you have to do, just plug in the numbers and that'll be it. The mass that we have, it is 1.5 times the radius is 0.33 squared. Don't forget this squared only for the radius. Multiply by omega final, it is going to be 0 because this is to stop. And then omega initial, it is 98.7. It is already in radian per second, so no conversion needed. Divide by the time, which is 2 seconds. All you have to do is just do the math, and you will find the answer, and it's going to be this much Newton meter. But of course, it's going to be negative because it is going to slow down. Okay, that is the answer for this one too. Now, I think it's time to move on to another question here. Okay, this question is also very interesting here. Let's solve this one too, because I like this question. It says, a bicycle exerts a constant force of 40 Newton. Let's get the whiteboard again. Okay, so here it says a bicycle exerts a constant force of 40 Newton. So we have a force of 40 Newton, that is first, on a pedal that is 0.15 here. So we can say this is the radius, 0.15. If not, you could call it the distance 2, makes no difference here. 0.15 meter from the axis of rotation of a bicycle wheel here. With a radius, so now it talks about the bicycle wheel with a radius. So here's the bicycle wheel. The radius of the wheel is 50 centimeter. If I convert to meter, that'll be 0.5 meter. And then if the speed is 2.25 meter per second, don't forget this is so obviously this is translational speed. You have to convert this one to rotational. This is translational. So we can say translational here. After it has, or after he started from rest. Now, I need you to remember this. So this is tangential. Now, if it is starting from rest, that means V initial is 0, and this would be V final here. Okay, so let's write it down. So this is the radius. We can say V initial is 0 because started from rest, and then V final, it is equal to 2.25 meter per second. Okay, it says after started from rest, 3 seconds after started. So delta T is 3 seconds here. Okay, I'll just write S for second. Okay, the question says, what is the moment of inertia of the wheel in here? Okay, now we know that net torque. How do I know? I'll have to use this equation because you have the force and distance. By using this too, of course, you can find the net torque. And because I have these initial and final stuff, I can use this one to find angular acceleration. But you have to be careful at this point here. We said F net is equal to moment of inertia times angular acceleration. Yes. Now, the question says find moment of inertia. So find moment of inertia here. How to find moment of inertia? Make it the subject and then bring this angular acceleration under this. So moment of inertia is equal to net torque divided by angular acceleration. But here's a problem. Do I have... I think it should have been way better if I just write a few things here before we remove this one here. Because I don't have the net torque, or I have force and distance. How can I find the net torque? Force and distance. It is equal to moment of inertia is unknown. Angular acceleration for this one, you have two choices or two ways to find angular acceleration. Because these are given in translational, first I can find, watch this, first I can find tangential acceleration, which is equal to V final minus initial divided by delta T. Whatever the acceleration, I'll have to convert it to angular. And how do you do that? It is equal to tangential over the radius. That is one way. What is the second method here? I'll have to convert these translational quantities into angular quantities. If V initial is 0, that means omega initial is also 0. Because whatever it is the same. Now, V final is this much. I'll have to convert this one to omega final. And how can I do that? You already know that. V tangential, that is equal to angular times the radius. True, if I want to find angular, what is it equal to? Angular speed final, that is equal to V final divided by the radius. What is V final? It is 2.25. That is the second method, by the way. Divide by the radius. And what was the radius? The radius of the wheel, it is 0.5. If that is the case, it is going to be 4.5 radian per second here. So now, if you found omega final, all you have to do, you could just plug in these numbers into the equation. Well, if that is, or in that case, if that is the case, we can say omega final minus omega initial divided by delta t. Now, that is the only unknown which I can easily find it. Yes or no? Very good. So let's just do that. The force that we have, it is 40 Newton times the distance is, let's just expand the whiteboard and then make this one a bit smaller. Okay. But if we just move this one to this point here. Okay, now we have enough space, I believe, to do this. Let's just move this one a little bit here as well. Okay, so now the force that we had, okay, the force is 40 times the radius, by the way, this is for the pedal arm, which is 0.15. It is equal to moment of inertia, it is unknown. Just write it unknown here. And then omega final, we just found it was 4.5 minus 0 divided by, what was the time? It was 3 seconds. Okay, so all you have to do, just find these numbers now. 40 times 0.15, that is 6. It is equal to moment of inertia. It is unknown. And that is 4.5. You could just divide it by 3. It is equal to 1.5 in here. 1.5. So how do you find moment of inertia? I believe everybody knows. Okay, so we can say moment of inertia, it is equal to, just divide both sides by 1.5, or 1.5 move it to under 6 or whatever. So 6 divided by 1.5, that is going to be 4, I guess. So 6 divided by 1.5, it is equal to 4. So we can say moment of inertia is 4 kilogram meter squared. This is how you can find the answer to this question. The most important thing is you need to know what is given and what is required as well, and how you can, these are translational, remember to convert this into angular, and then you can easily find this one, and that'd be the whole thing. There's nothing complicated about this if you follow the steps carefully, the equations, everything that you need to. We have this question too, also been in Uzari. It is an interesting question as well, and of course, we can change this question too. What does it say? It says 2 uniform solid cylinders of equal radii roll down an incline without slipping. All right, the first cylinder has twice the mass of the second cylinder. Now, how much torque was applied on the first cylinder compared with the amount exerted on the second cylinder here? Now, this question is interesting as well. So we have 2 cylinders. They're both rolling down an incline here. Okay, so here's one, this is another. These are both rolling down an incline, but the mass of the first one, so here's this, and this is the second. Let's call this one first and call this one second. The mass of the first one, it is twice as the mass of the second one here. So whatever the mass of this one, the mass of the first, that is going to be 2 times that mass. So for example, if this is 5, this is 2 times 5, that would be 10. So how much torque is applied or exerted on the first compared to the second one here? Now, regarding the torque, we know that torque is equal to moment of inertia times angular acceleration. And we can simplify this further. It is equal to a fraction of constant times mass times radius squared times angular acceleration. Now, we know that torque and mass are directly proportional. Yes or no? Based on this, so we can say torque, it is directly proportional to the mass. That is one big fact you can say. Okay, so now regarding the answer, or to answer this, the question now says how much torque exerted on the first cylinder compared to the second. So can I say the torque, because this one has twice as mass, right? So can I say the torque of the first object, first cylinder, must be 2 times the torque of the second? The answer is because this one has twice the mass of the other one. So the larger the mass, the larger the torque. The torque of the first one must be 2 times as large as the torque on the second one over there. But that is, the question says just how much torque exerted on the first compared to the second. But you really have to be careful here. And one of these, my questions here, I've brought this as a question. I said how much torque is exerted on the second cylinder, let's say, compared to the first. So if you're not careful, you might make a mistake in here. So if the question is asking how much torque exerted on the second compared to the first, so make the second the subject, and that is going to be 1/2 of the torque that is exerted on the first one here. So if the question is asking about the second, we can say the torque that is exerted on the second cylinder, the second object, it is going to be half of the torque that is exerted on the second because the mass is half of that, you could say. Now let's get back to this one here. So these are what we have. Remember, the mass of the first is 2 times the mass of the second. So the torque of the first one, it is 2 times the mass of the second one as well here. Okay, that is what we have. So we can say the torque of the first is this much, but if they ever ask for the torque of the second object, that is half of the torque of the first one. Why? Because these two are directly proportional. Okay. So you have to be aware of that as well. There was another question. This one is also very easy. It says a 30 kilogram solid cylinder. Don't forget, solid cylinder is the same as a disc, which is 1/2 times mass times radius squared. It has a radius of this much. So this is the radius. Okay, 0.180 cylinder. All right, if the cylinder, that is the, by the way, that's the radius in meter. If the cylinder accelerated with this much, that is angular acceleration, as it rotated about a fixed axis through the center, how large is the torque acting on the cylinder? Well, that is pretty easy. The torque with the net torque is equal to moment of inertia times angular acceleration. But since we have a solid cylinder, that is 1/2 times the mass times the radius. The mass is 30. The radius is 0.18 squared times the angular acceleration, which is 2.3 times 10 to the power -2. Just do the math. You'll find the answer in Newton meter, and that'll be it. Okay, so this one pretty easy as well. Now this question is also interesting. It says a 350 kilogram merry-go-round in a shape of a disc. Don't forget this. Whenever it gives you these shapes, make sure you underline these shapes because you need moment of inertia. The shape of a disc it is, or moment of inertia of a disc, it is 1/2 mass times radius squared. Always, you can see that I've made them bold so that you know it is a keyword. You will need this one. But you, for yourself, you can always underline this and write the equation right away, just in case if you need the equation. Okay, so the radius is 1.5 meter. It is set in motion by wrapping a rope around the rim of the disc and pulling on the rope. The question says how large a torque would have to be exerted to bring the merry-go-round from rest. That means omega initial is 0 to an angular speed of. So this is going to be final in this much time. So this is delta t. Okay, so once again, moment of inertia, where you could say the net torque is equal to moment of inertia times angular. The question says how much torque, yes? So the net torque is unknown here. So the net torque is equal to moment of inertia, since this is the same as the disk, times radius squared times omega final minus omega initial divided by delta t, yes? You have the mass, 350. You have the radius, which is 1.5 squared. And then omega final, it is going to be 3.14 radian per second. Radian per second, no conversion needed, divided by the time, which is 2. And then just do the math. You can find the answer, which is going to be in Newton meter. Okay. This question, which is also interesting. It says, it is more difficult to do sit-ups with your hands held behind your head than doing a sit-up with your hand or with your arms stretched out in front of you. Explain why. Now, this question is more specifically for those who go to the gym and do sit-ups. Have you ever noticed why if your hands are held behind your head, it is more difficult to do the sit-ups? But if it is extended, or let's say if it is brought close to your chest, it is easier. Why is that? So first of all, let's just draw a diagram. Hopefully the diagram, okay, let's say there's a person here. Not enough. Okay, let's try something maybe better. Okay, imagine this is a person. That's not a real person, right? Now at this point, the hands are held behind the back, just like this one, for example, okay? If the hands are held behind the back, what exactly do you think will happen? Let's say this is the center or the axis of rotation. The mass will be far from the axis of rotation, is that true? Or will be distributed far from the axis of rotation. We've learned that in moment of inertia. We said if the mass is far from the axis of rotation, and if that is the case, then what do you think will happen to moment of inertia? Well, moment of inertia, of course, it is going to increase. If moment of inertia is going to increase, then the angular speed will be smaller. In other cases, it is going to be very difficult to rotate. That is the first case in here. But what about the second case here? Now, the same person, obviously lost some weight, maybe the second case. No, that's horrible. Okay, that's the person here. Okay. Now, this time, the arms are extended or the arms are closer here. You can even extend them. That's totally fine. This is the axis of rotation. You can see that the mass this time, it is closer to the axis of rotation. Is that true? If the mass is closer now, we know that at this point, let's say the mass is closer. How do we say the mass is closer to the axis of rotation? All right, let's just say the mass is close. All right. I meant by writing a diagram here. So the moment of inertia is going to be smaller. If that is the case, angular speed will be larger. In other words, it is going to be easier to rotate or to do the setups at this case here because now the mass is closer to the axis of rotation, which is obviously, you can say, from the hip. This is the reason why the mass is far, larger moment of inertia, more difficult to rotate. The mass is closer to the axis of rotation, so less moment of inertia, easier to rotate. This is why it is easier. Normally, once you have a lot of energy, like at the beginning of the training, then you do or held the hands behind the head. But then once you get tired, of course, you bring them forward or closer, because now it requires less energy to do that. Okay, so this is the reason why. So once again, performing a setup with your hands held behind your head, it is more difficult. Why is it more difficult? That is because the mass of your body, you can see, the mass of your body is, let's pin this. All right, so now the mass of your body, you can see, or this because the mass of your arm is distributed far from the axis of rotation, which is your hip, resulting in a greater moment of inertia that requires more torque to rotate your body. This is why it is difficult. All right, now I think it is time to answer a few anxiety questions maybe. Says in the equation, what does I stands for in here? First of all, let's just get rid of or clean this one a little. Oh, this is supposed to clean. Okay. Says I in the equation net torque moment of inertia times this. What is it called? It is called moment of inertia, right? Which of the following equations are not true to find the torque? Torque equal to moment of inertia times angular acceleration. That is correct. Torque equal to moment of inertia times angular speed. We don't have this. So this is the answer that we're looking for. Torque equal to f d times sine theta. That is also correct. Torque equal to moment of inertia times change in angular speed over the time. That is the same as saying angular acceleration. So this is also correct. So the one that is incorrect here, B. So B is the answer that you need to circle. All right. 3 says, according to Newton's second law, in the case of rotation, the angular acceleration of a body is directly proportional to which one of the following? You have to be careful here. And the best thing to answer these questions is to write the equation. All right, according to Newton's second law, what does Newton's second law say? It says the net torque that is equal to moment of inertia times angular acceleration. All right, then it says the angular acceleration of a body is directly proportional to what? Make angular acceleration the subject. So angular acceleration, it is equal to net torque over moment of inertia. We know that anything above the fraction is direct, anything below is inverse. So now the angular acceleration is directly proportional to what? To the net torque, and it is inverse with the moment of inertia. Let's see if we have one of those. It says the moment of inertia of the body, no, because it is not direct, it is inverse to that, so no A, not A. The result of the applied torque, that is true. Okay, but let's, the body's volume, no. The body's mass, no, because it is inverse with the mass, because moment of inertia is equal to factor certain number times mass times radius. Okay, now question 4 here. Something there's a yes, 4. Which of the following statement is correct? Also, I think it would be best if you perhaps maybe write some stuff for yourself. It says, with a net positive torque, the angular acceleration of an object is clockwise. If you remember, we said when we talk about net torque, okay, we have positive and negative torque. We said all the examples that we have, the book considers all the types of rotation is counterclockwise. Counterclockwise in here, where the angular speed, we can say it is positive. If that is the case, with a positive net torque, the angular acceleration, if the net torque is positive, the angular acceleration must also be positive. Okay, but here says the angular acceleration of an object is counterclockwise. That means negative. Is that true? The answer is no. Right, so not A. B says with a net positive torque, the angular acceleration of an object is, my bad. The first one, I've switched with this. Let me go back to A. It says, with a net positive torque, the angular acceleration of an object is clockwise. Well, if the net torque is positive, can the acceleration be clockwise? The answer is no, because the angular acceleration must also be counterclockwise as well. But, sorry, if it is positive, yes, if it is positive, it has to be counterclockwise too, but this one says clockwise, which is incorrect. B says, with a net positive torque, the angular acceleration of an object is counterclockwise, and that is correct. If the net torque is positive, then the angular acceleration is positive, then omega final must be bigger than omega initial, and we said that we consider the object is rotating counterclockwise, so the object must be moving counterclockwise, so we can say B is correct. What about C says, with a net negative torque this time, if the torque is negative, we've mentioned previously, the angular acceleration is negative, which means that omega final must be smaller than omega initial. But let's see what it says. With a net negative torque, the angular acceleration of a body is counterclockwise. No, if it is counterclockwise, it is going to speed up instead of slowing down, which in that case does not make the net torque negative. All right, D says, the net force on an object is not related to the translational acceleration given at that object. That is also incorrect. Why? Because the net torque, it is equal to moment of inertia times angular acceleration. But if I did not have angular acceleration, can I say net torque, it is equal to moment of inertia? Instead of angular, I'll just write tangential over the radius. Isn't that also correct? So what is the relation between these two? Aren't they directly proportional? This one says it is not related to translational, right? That is incorrect. So the only correct answer is option B here. All right, question 5. It is repeated. It is the merry-go question. Maybe sometimes they'll give different numbers. Sometimes it is exactly the same number. I'll try to solve question perhaps maybe 6 as well. I don't like to make this one any longer. So let this perhaps be the last thing that we do for this session. Not this. Question number 6 says, a force of magnitude 4 Newton applied tangentially to a disk. What does it mean tangentially to a disk? And you really have to be careful here. Like I've mentioned earlier that if this is a disk, this is the center, This force that is acting on the disk here, you can call this one F tangential. What is the magnitude or the size of the force? 4 Newton. Tangentially to disk, but at diameter. Don't forget, instead of the radius, the diameter is given, which is 0.2 meter here. And we know that if we ever want to find the force, we'll have to find the radius, because always the center of the disk would be the axis of rotation when this thing is going to rotate here. So if we want to find the radius, that is equal to diameter divided by 2, that is 0.2 divided by 2, it's going to be 0.1 meter. That is the radius of the disk at this point. Okay, says if the angular acceleration of the disk is 8 radian per second, what is the mass of the disk, and u is moment of inertia equal to this much. All right, well, the net torque, it is equal to moment of inertia times angular acceleration, true? So the net torque here, it is equal to force times the radius, not the diameter. Moment of inertia, it is equal to, since it is a disk, 1 over 2, it gives you the equation 2, that is a good thing. Mass times radius squared times the angular acceleration. The question says find, my bad. We have the angular acceleration, yes, which is 8. The question says find the mass. The mass of what? The mass of the disk. So let's do that. But I believe at this point we'll have to expand this one a little. All right, so once again, the force is 4, the radius is 0.1, it is equal to 1 over 2, the mass is unknown, the radius is, once again, times 0.1 squared times 8, correct? That is going to be 0.4, that is 8 and 1 over 2, that is 4, times 0.01, we can say times the mass, yes? That is 0.4, it is equal to 0.04 times the mass. So what is the mass equal to? 0.4 divided by, and out of all these spaces, huh? Okay. So the mass, both sides divide by 0.04. These two cancel out. So the mass equals to 0.4 divided by 0.04. That is going to be 10 kilogram, correct? Let me write this one a bit nicer. 0.4. You can multiply each one of these by 100. That is going to be 40 over 4, which is 10 kilograms. So this is the mass of a disk. Let's see which one of these options is 10 kilogram. Okay. All right, it was question number 6, right? So it is option D. I was almost, okay, I was looking at 7. I was a bit surprised. Okay, so this is 10. So the correct answer is option D. I believe 7 is easy. We have a force, we have a mass, we have the radius. What is the angular acceleration? This is way easier than the other one. Once again, you can see that this question's been repeated. I told you like this been in Uzadi several times, so make sure you know how to do this one. The last question that I want, so you could try this on your own here. I would rather try to solve question 9 here. So what is question 9, or how, if you ever been or you see a question like this in Uzadi, how would you answer this question here? Okay, so let's do this one. It says a thin rod of length L all right, a thin rod, all right, we have a thin rod of length L, so here's a thin rod, the length of this thin rod is L, and it has a certain mass, you can say. Okay, it says it is pivoted at one end, so one end would be the axis of rotation, that is what it means here. This is the axis. The next thing says, if a force F is applied perpendicularly at a midpoint, this midpoint, it is a keyword, that means right at the center of this. That would be the midpoint here, like middle point. That's what it says. So here, a force is applied at the midpoint here. And then the question says, what is the angular acceleration? If a force is applied at this, clearly this one is going to rotate. What would be the angular acceleration of the rotation of this thin rod here? Now we know that F net, it is equal to moment of inertia times angular acceleration, correct? Now, the question says, what is the angular acceleration? So F net that is equal to force times the distance, but instead of the distance, we have the length in here. So we'll just say the length here. But there is one thing you really have to be careful here, because it says midpoint. So whatever the length of the thin rod is, this distance, it is going to be half of that. So can I just use half a length here? Because the whole thing is length. Midpoint would be half of that. So I'll write 1/2 of the length in here. Now, what about the moment of inertia for a thin rod about the end, if you remember this, right? So it is equal to 1/3 times the mass, which we use M capital here, times the length squared, and then equal or multiply by the angular acceleration. Now, one of the length cancel out with this one here. Now, all you have to do just cross multiply. All right, let's expand this one too, I guess. All right, so what is left at this side here? That'll be F/2. On the other side, we have mass times 1 length divided by 3 and then multiplied by angular acceleration. So make angular acceleration the subject. Well, all you have to do is just cross multiply. This 2 would go under, this one goes above. So we can say angular acceleration, it is equal to 3 times force and divided by 2 times the mass multiplied by the length of the rod in here, and that is the correct answer. Okay, so let's see which one is this. Don't forget that is 3F/2 times the mass times the length. 3F times or divided by 2 times mass times the length here, and that'll be the correct answer. And if you see the same option here, of course, you can change one of this 2 to 4, because in some of the I believe for most of you, this number is repeated here, 3F divided by 2. Just make this 2, 4 so that you have different answers. And if you see answer both A and B the same, you could just choose one, makes no difference. But this is how you can do that. I believe that was the last thing for today. Next time, inshallah, we're going to start with this example. Also, this one was added recently, so I hope you stay with us until we solve this one too. Till then, keep practicing, and I'll see you soon, inshallah. Assalamu alaikum wa rahmatullah.